data that the lander's computer automatically knows is bad information. Collectively, the DDL screen is one of many data displays that flight controllers are monitoring to successfully navigate NOVA-C to the lunar surface.
Data visualization is an essential component for flight controllers who need to process this data for real-time decision-making in NOVA Control. Now again, we're following along with the flight control teams here in NOVA Control prior to the next critical steps, including activation of the navigation Doppler LiDAR to provide guidance, navigation, and control for the landing phase. This is expected around 4:45 p.m. Central Time. The next critical milestone is powered descent initiation at 5:11 p.m. Central. This burn is the first in a sequence of maneuvers that starts about 12 minutes prior to landing, or about 50 minutes from now. NOVA-C is, of course, landing on the moon as a delivery truck for the scientific instruments and technology demonstrations on board. There are 12 total payloads, 6 of which are NASA's. Let's review a few of those payloads as we continue to descend towards the lunar surface. First is radio observations of the lunar surface photoelectron sheath, or ROLSes. ROLSes will employ 4 antennas and a low-frequency radio receiver system to determine the density and scale height of the moon's photoelectron sheath, a very thin layer of electrons above the surface of the moon, and will also detect solar radio bursts, radio emissions from Jupiter, dust impacting the surface of the moon, and how radio noisy Earth is.
An exciting radio telescope is going to be placed on the moon. It is called ROLSes. It stands for radio wave observations from the lunar surface of the photoelectron sheath. It's going to detect all kinds of radio emission that is falling on the moon. Right now it is close to solar maximum, so the sun is producing a lot of coronal mass ejections and radio emission associated with them, and we can detect these radio bursts from the sun. Characterization of the radio environment of the moon is very important. It has not been completely done, and therefore ROLSes will be able to contribute in identifying various sources of radio emission on the sun. If you're setting up an observatory on the moon, we should know what kind of radio interference we get there.
The Laser Retroreflector Array, or LRA, is a collection of 8 retroreflectors that enable precision laser ranging, which is a measurement of the distance between the orbiting or landing spacecraft to the reflector on the lander. LRA is a passive optical instrument that will function as a permanent location marker on the moon for decades to come.
This is a little mirror that's aiming at you all the time, regardless which way you're looking at it. My name is Xiaoli Sang. I'm a LiDAR instrument scientist. It's a small retroreflector mounted on an aluminum shell on the Intuitive Machine landers. When you shine laser on it, it reflects right back at you. The purpose is to have a precise fiducial marker on the landers. It serves as a landmark for future missions if you want to go back and land it there.
Stereo cameras for lunar plume surface studies, or SCALPs, will use a suite of 4 cameras to capture stereo and still image data of the dust plume created by the lander's engine from when it begins its descent to the lunar surface all the way down through engine shutoff.
SCALPs is an array of small cameras that will be placed around the base of a lunar lander and collect imagery during the descent and landing of the vehicle. Using a technique called stereophotogrammetry, we can use those images to reconstruct a 3D shape of the ground. As the lander comes down, its hot engine plumes will interact with the surface. Our cameras will begin acquiring images from before this interaction begins until after the vehicle has landed on the surface. The SCALPs cameras will specifically be looking at the overall crater formation and erosion of the ground due to the rocket plumes. The final stereo images, which will be stored on a small onboard data storage unit, will be transferred to the lander and then downlinked to Earth, where we can use them to reconstruct the overall erosion volume and shape of the ground. With the Artemis program, we plan to establish a sustained lunar exploration and try to land multiple payloads in close proximity to one another. SCALPs data will be a critical part of understanding these phenomena and improving our computational models to inform these future landings.
Radio Frequency Mass Gauge, or RFMG, is a fuel gauge used to measure the amount of propellant in spacecraft tanks in a low-gravity space environment. Using sensor technology, RFMG will measure the amount or mass of cryogenic propellant in NOVA-C's fuel and oxidizer tanks, providing data that can help predict fuel usage on future missions.
I'm Greg Zimmerly, the principal investigator for the Radio Frequency Mass Gauge payload. This instrument is a space-age fuel gauge. We're going to use it to measure the amount of cryogenic propellant in the Intuitive Machines NOVA-C Lander propellant tanks. These propellants are very cold. They're at about -300 degrees Fahrenheit. Now we're integrating the instrument onto an actual lunar lander. Future lunar missions, like those in the Artemis program, will likely also use cryogenic propellants and have to store those propellants in space for long periods of time. So having an instrument like this that can measure the propellant in the tanks in low gravity will help future lunar missions know how much fuel is in the tank at all times.
Now we'll discuss two more NASA payloads, Navigation Doppler LiDAR, or NDL, and the Lunar Node 1, or LN1, later during our broadcast. We'll have a special guest later in the broadcast to talk NDL upon its activation during descent. And Josh, we did get word that some of the processing of the optical images from NDL are already performing. They did some checks, and they're performing very well. Now, a common theme you'll find among the NASA payloads on IM-1 is helping to demonstrate technologies and our understanding of the lunar landscape that could very well improve operations for landing on the moon in the future. From understanding the environment to precision sensors to literal beacons, the technology on IM-1 will help guide technologies and operations for future lunar exploration.
And Gary, with CLIPS as a springboard of innovation, Intuitive Machines designed and developed its complete lunar program to help support CLIPS and carry out the essential part of that directive, which included calling for the commercial development of the moon. Back in 2018, the U.S. government declared the moon of strategic interest. At that time, few companies and institutions were working on payloads designed for the moon because no one had been to the lunar surface in over 50 years. Gary, in the time it takes to get an undergraduate degree, 6 commercial entities created payloads for the IM-1 mission. We'll view all of them as pioneers helping shape this brand new lunar economy.
And Josh, a true lunar economy should not have just NASA as a sole customer. NASA's CLIPS initiative encourages a model where NASA is just one of many customers. And this is an important element to ensure that this model of transporting incredible science and technology instruments to the lunar surface is a sustainable and robust one.
Well, it's important, and Gary, it's also promising in this situation. The commercial interest for delivering science and technology demonstrations continues to grow. As of our third planned mission, we're seeing more and more non-CLIPS payloads from both domestic and international companies and institutions, which are driving us towards a future, maybe completely commercial mission to the moon, possibly as soon as our 4th mission.
Well, even on IM-1, there is a variety of unique commercial payloads. It's a good snapshot of out-of-the-box ways to think about what the moon can offer.
Well, that's part of the challenge. Beyond just creating the capability to land on the moon safely, we had to look toward a new emerging ideas and find innovative ways that may add value on Earth and spaceflight. Let's learn a little bit more about those payloads and the lunar lander attempting to make history.
The NOVA-C was our version of a liquid oxygen, liquid methane lander, and we went about imagining that into existence.
Intuitive Machines' NOVA-C class 3D printed engine took its first breath of liquid methane and liquid oxygen in 2018 on an airstrip at Ellington Airport in Houston, Texas.
We didn't have enough money for a facility with blast walls and water suppression or water deluge, so we had to test outside in the environment of Houston, where the temperature is about 100 degrees and the humidity is like the same, and we have an 18-hour day rolling out to the runway. It was brutal. but we did it to get the critical test engine data we needed to build our own engine.
Designed, manufactured, and controlled in space by Intuitive Machines, NOVA-C's structure is primarily carbon composite.
We needed to build the lightest weight structure we could. That meant honeycomb aluminum core with composite face sheets, composite struts, and most importantly, linerless composite propellant tank. Man, what a challenge that was.
Between the engine, carbon composites, software, and electronics required to build a NOVA-C lunar lander, it took an incredible amount of touch labor to get to the launch pad.
We worked very closely with San Jacinto Community College to create a certification course for technicians, where they would take these certifications. We then at Intuitive Machines would give them an internship and test them out in the workplace. And anyone that showed the aptitude to be a really good technician, we hired on the spot.
Nearly all of the lunar lander's payloads are mounted to its exterior, including 6 NASA-provided payloads that will help lay the foundation for Artemis missions. Embry-Riddle Aeronautical University's EagleCam, designed to deploy off NOVA-C right before landing to take third-person perspective images. The International Lunar Observatory Association's camera system, mounted at exact angles that could capture images of the Milky Way from the lunar surface. A data center technology demonstration by Lone Star Data Holdings, and Omni Heat Infinity, Columbia Sportswear's thermal reflective insulation used in many of their outdoor products, will help protect NOVA-C from extreme temperatures in space.
They've got brilliant ideas, and if we can help facilitate those startups to help build this economy, I think that raises all boats, and it's as serving as the transportation leg to the moon, we're happy to accommodate those kinds of companies.
Now, the lander and our payload customers require command and control in space. Intuitive Machines' Mission Operations Center provides both of those elements. It's called NOVA Control, NOVA being the name of our lunar lander class, and Control being the nerve center of our entire lunar program. Its unique circular design fosters a collaborative environment where flight controllers and customers may make agile decisions. Let's take a live look.
Yeah, and inside that flight control room, Josh, it's important to note that these are not the only teams that have been in this room over the past 7 days. This is staffed 24/7 inside in NOVA Control here. There's red, white, and blue teams that support this mission.
Gary, the mission required 24/7 operations. We're somewhere in between the 7th and 8th day. This has been 3 teams, red, white, and blue, working 8-hour shifts, which really turned into just about everybody working 12-hour shifts each. In addition, there's another team, the gold team, that's running problems and solving solutions that are coming up in the future. And at this moment, we talked about this being a dynamic situation, using 2 of NDL's lasers to feed into our HRN and TRN cameras to provide a landing solution. Every asset available out of all of these teams is on hand right now to solve these intractable problems and take the best shot at the moon we possibly can.
It really took a team to solve some of these. As you mentioned, a dynamic situation. Now, you talked about the design of this room, fostering that collaboration. It's a little different from what I'm used to over at the International Space Station Flight Control Room, where you have consoles that are facing towards large screens. What exactly is the logic behind this particular design?
Really, we wanted to get everybody together into where we're a small company. There's not a lot of us. Agility is our strong suit in this situation, and this room really suited us. It's a situation where we can put our payload customers inside the center, or let's say we need to bring in operators who have knowledge of the things that need to happen in the future that we haven't quite touched on as a team, but you can insert those folks into the center of this room, make quick decisions, respond to problems, and that's really the way that we see tackling some of the hardest challenges in the world. And certainly right now for us, this is one of the hardest challenges on the moon, most certainly.
Which we are saying absolutely, and it takes everybody in this room, and everyone has their respective roles, just like we see with any spacecraft. Each of these individuals provides insights into a specific spacecraft subsystem.
And the captain of this whole thing is usually the mission director. In this case, this is Blue Team. That is Dr. Tim Crane. He's our co-founder and chief technology officer, serving as mission director today. Now, flight control operators continue to monitor NOVA-C's performance. Operationally, we're still counting down to PDI ignition at 5 5:11 p.m. Central Time and landing at Malapert A at 5:24 p.m. near the south pole of the moon. For more on Malapert A, let's head over to Leah Cheshire. Leah?
Thanks so much, and I am now here with Ben Bussey, Intuitive Machines Chief Scientist, to talk about Malapert A. Thank you so much for joining us, Ben.
It's great to be here.
Now tell me a little bit about this landing site. Why was it chosen? What sets it apart?
So the most important factor when selecting the landing site was to find a good, safe site for Odysseus to land. And we're landing in highland terrain near the poles, and that was a fun challenge for the team. But we think we found a good, large, safe area